Alrighty, hey there, everybody. Welcome. Alrighty, hey there, everybody. Welcome to the RSN Spring Conferences presented by WPI. I'm Francis O'Rourke. I'm your host today. We have a lot of content coming up in the next 5 days. We just finished our first presentation by Jared from the Milken Knights. He did a great presentation on the psychology of first and making your own luck. You'll be able to check that out on YouTube pretty shortly, and it's archived on Twitch right now. But right here, right now, we've got our next guest coming up. This is Tyler Veness. Tyler, why don't you tell us a little bit about yourself?
Hi. So I'm a WPILib developer. I've been working with them since around 2015 or so. I am a graduate of University of California, Santa Cruz. I got a degree in robotics engineering.
Oh.
I was on FRC team 3512 for the 2012 and 2013 seasons, and I've been mentoring them ever since.
Very cool. All right. Well, Tyler, thank you so much for joining us. Today, you're going to be presenting about model-based validation of autonomous modes, autonomous driving using the WPILib. I took a look at your presentation. It's got a lot of math involved, but I'm pretty sure you're going to be able to deliver it in a way that everybody's going to enjoy and understand. So I'm looking forward to it.
And feel free to ask questions if you have them.
Yes, excellent point. If you have questions, go ahead and ask them in the Twitch chat using the !Q command. If you ask your question, we'll pull it down and save it, and the great ones we'll send over to Tyler for him to answer live during the presentation and also at the end after we're all done. But before we get started, I want to say one more word. I want to thank the people who helped make this possible, and that is WPI. WPI, or Worcester Polytechnic Institute, is a leader in project-based education and is the first university to offer a BS, MS, and PhD in robotics engineering, which is something Tyler just mentioned. If you want to learn more about becoming a student, sponsoring a project, or anything else, you can just visit wpi.edu for more information. Now, on top of that, WPILib, the thing that all of the first box competition teams use to program their robots, that is developed through WPI. So for more information on that, you can also visit wpi.edu/plus-first, or just Google WPILib and it'll show up for you, I'm sure. So, All right. Well, Tyler, with that out of the way, I invite you to go ahead and take us away and tell us more about your model-based validation of autonomous.
Yep. Right. So today we're going to be covering autonomous driving, but since a lot of teams don't have access to a robot, we're going to get in some of the math behind these robots so that we can model them mathematically and test our stuff without robots. My team did a lot of this last year, so some of that's going to be from stuff my team did.
And really quickly, Tyler, just to get an idea, you can also do this when we're back in sort of the normal times, right? Even when you have access to your robot, you can still model things, for example, before the robot's finished being built, right?
That's right. And that's one of the best things about this is that you don't need to wait for mechanical to finish their robot in week 7.
7? That's early.
Yeah, right. So you can model everything, including your sensors, like how the mechanism moves, and then you can test all kinds of things, like not just your controllers, but all your logic, like all your state machines, so that you can get all of your bugs worked out much earlier, so that when you put it on the hardware, you're just making sure all the motors and the sensors go the right way. So in autonomous driving, there's a couple different types that you usually see, right? So you have, teams that don't move, which is really unfortunate because programming robots is hard, and we want to make that as easy as possible. You see time-based, where you're driving forward for some distance. Francis, you there?
Oh, yep, I'm right here.
Okay.
Yep.
Cool. So time-based, so you set the motor to a voltage, and you drive forward some amount of time, and then you stop. And then you get even more complicated. So you get like trapezoid profiles. So you like speed up for a bit, you cruise at that velocity, you slow down again, then you turn, and then you drive forward again. And that lets you correct for, like, make things more consistent, because you're moving how the drivetrain can actually behave instead of just, full forward, full stop, and you're actually using sensors.
Okay. When you say spline based or trapezoid based, do you mean is that like a graph of the velocity of the robot or something?
Yeah,
okay.
And I'll have some slides later that go into exactly what those are.
Excellent.
Yeah, and then spline based, you have, like, instead of stopping and then turning, like, you have a smooth curve that takes you from point A to point B. And that's what we're going to be showing today, because starting in 2020, like, we have support built into WPILib to make that possible.
Is that I know you're probably going to cover this, but is that like the Pathweaver stuff I've seen, or?
Yes, that's Pathweaver, and then there's trajectory generation libraries.
Very good.
So yeah, first we're going to introduce some of the basic concepts. So we're going to introduce localization, which is how you figure out where your robot is. Motion planning, where you figure out, based on where I am, how do I get to where I want to go? And then control, which actually gets you there. And we're going to show this using the WPILib 2020 features. And then towards the end, we're going to show a demo using my team's robot code, because we have the whole drivetrain simulated. So localization is this term that means to use external measurements to figure out what your drivetrain's position and orientation on the field is. We call that a pose. So you have, in two-dimensional space, your X position on the field, your Y position on the field, and your heading, so like which direction you're pointing. And you can use measurements like your gyroscope and your encoders to figure out where you are. And once you know where you are, where you're going to be going, like using successive measurements over time.
So, and pardon me for interrupting, but a lot of what I've done in smaller robot, I am myself not a controls programmer for FRC, but I've done a lot of smaller robots. Is the prevailing method using encoders and like the gyro, as opposed to trying to use like external ultrasonic sensors to sort of find landmarks, or is that a whole different sort of theory behind it?
So they all follow under the same umbrella.
Okay.
And there's a couple different ways you can figure out where you are. All you need is a mapping from what your sensors say to what your pose on the field is. And that could be range of measurements to an object, if you know where that object is. That could be like a gyroscope that tells you your heading, like, directly.
Mm-hmm.
You could use computer vision that'll tell you, okay, this target is over here. And then based on the way this target looks, I must be at this point on the field. And that's called perspective end pose, perspective endpoint.
Okay.
And that's getting more popular nowadays, now that things like FRC vision exists. And in the past, teams would use ultrasonic sensors, because a lot of when you're using encoders to figure out where you are, you need to do some math to like take the difference between your measurements and compose them together to get where you are. And a lot of teams don't know how to do that. So what we did last year was we added libraries that had that math prepackaged. So all teams have to do is throw encoder and gyro measurements into it, and then it gives them the robot position.
Sick. And like you said, this is all already in WPILib, just waiting for people to use?
Yes.
Cool.
And there's tutorials and documentation as well.
And before we go too deep into it, is there any difference between what you're presenting with respect to whether you use Java or C++ or LabVIEW or one of the other, we'll call them secondary languages?
So we have first-class support for C++ and Java for both of these libraries. I believe there's a third-party port for LabVIEW.
Okay.
That I saw on GF Delphi. The stuff I'll be showing in this presentation will be C++ because that's what I'm comfortable with. But C++ and Java are pretty similar, at least when you're doing things the idiomatic way.
Okay.
Right. So there's a couple different ways you can do what's called odometry, which is the process of taking your encoder measurements and your gyro measurements and getting your position. The simplest way is using what's called Euler integration. So what you're doing is you're taking your current position, which is denoted by that underscore k there. K is some time step, like 2 seconds. And you take your current velocity and multiply it by a change in time. So velocity is the slope, and you multiply by the change in time, and you get an area, and you add that onto your position, because meters per second times some amount of seconds gives you meters. And so we do that for both the x direction and the y direction. Cosine gives you the x direction, sine gives you the y direction. And then your heading is just going to be whatever the gyro says it is. And so this is what a lot of teams previously used, because it's simple, works well. But we can actually get even more accurate, because with Euler integration, you're assuming that you're going in a constant direction between each of your time steps. So you got this line, like tangent to where you are, and then you go forward a little bit, and then you get a new angle, and then you go forward a bit more. But if your robot is, say, following a constant arc, that won't the Euler integration won't necessarily be as accurate, because this is assuming you're not rotating as you're moving.
I see. Because if you were doing that, you would basically have to approximate it with a series of like straight lines, right?
Right.
Okay.
And if you reduced your sample period, you'd get a closer and closer approximation, because your lines are shorter and shorter. But what we're going to do next is show how we can include the case where you have a constant turn radius, so we can get a more accurate reading. And the way we're going to do that is we're going to get our velocity forward, which is x. Oh, and the coordinate frame we're working with, I forgot to mention, x is forward and y is to the left. And because x is forward and y is to the left, when you do right-hand rule, angles are clockwise.
Okay.
Or counterclockwise. Positive. So what we're going to, so this is linear algebra. Don't let the notation intimidate you, right? So it's pretty similar to what we had before, but we're using more generalized language. So we'll start from the left side. So this thing with 3 rows and 1 column is a vector. We have 3 elements in it. We have a small change in x, which we call dx, a small change in y. So these are really small increments, as you're moving.
Right.
And then so you have one in x, y, and theta, where theta is the heading. And so the superscript g means global. So this is saying, I want to get a small increment for my change in my global position. And we want to use the velocity and the angular velocity to get there. So on the right side, you'll see that 3x1 vector. You have your x velocity, your y velocity within the robot's coordinate frame. So you have x is always forward in the chassis and y is always to the left in the chassis. And then omega is your turning rate. So this is pretty similar to what we had before, where you have your velocity time component times some time. And we're doing the same thing here. We have the velocity times some increment of time, dt. And then we're saying, okay, that's the velocity in the robot's coordinate frame, denoted by the capital R there. So how do we get from the robot's coordinate frame to the global? Well, we use a rotation matrix to do that. And what that says is that we give it some angle to rotate, and it's going to spin that vector there with your x and y components by some headings, so that you now have a like the X and Y components like in the global frame instead of the chassis frame. So like you think of like the gyro angle, and so you'd rotate by the gyro angle to get like from going forward. And then if you're pointing, say, 90 degrees to the left, then it's going to rotate all of your vectors, so that if you were going forward and facing like towards the other alliance wall, like that's an angle of 0. So there's no rotation. If you were to rotate 90 degrees, now your X component is pointing in the Y direction now, because you rotated by 90 degrees.
Okay.
So back to the rotation matrix. What we're going to do is take all of our vectors and we're going to rotate them by the angle at t. So we're going to go like start at like time equals 0, and then we're going to go at time at 0.1 seconds. And as you are rotating, because you have an angular rate, the omega, when you multiply by t, you get an angle back. Because remember that you take your rate, multiply it by time, you get a position. And this is angular position. So as we traverse forward in time, it's going to rotate your X and your Y, and then we're going to just add them all together repeatedly. And you can go through a whole bunch of calculus with integrals and actually solve this in a closed form, and that is what the thing on the bottom is. So after you add up all the small increments, you're going to get a change in your local position times a bunch of stuff with rotation matrices gives you a global change in position. And by the way, you won't need to know this for actually using the library. This is just background for those that are interested.
You know what, Tyler? That might be the best news I've heard all day.
Fair.
Now, to be fair, it's been a while since I've done myself. I've done any sort of like matrix linear algebra in a lot, but linear algebra itself is actually not all that complex. And what's going on is pretty easy to solve with something like Mathematica or Wolfram Alpha if you want to get crazy with it, right?
Right. And the concepts of linear algebra in terms of like linear transformations is not that hard to grasp. The 3 Blue 1 Brown YouTube channel does a fantastic job.
Yeah, I really love that channel. That's great.
Yeah. And so if you do want to get into like more of these like linear algebra and a lot of these equations here, I highly recommend looking at that video series, Essence of Linear Algebra, and then coming back to this, and it'll make a whole lot more sense. And so that's the odometry method we're going to be using. And then it'll be nicely packaged for you, so that you can take what your encoder measurements were in the X direction and your change in your heading, and it'll turn it into magically a global pose for you. And then next we're going to cover controls. So like how to get from where we were to where we want to be. And control theory is this whole umbrella discipline that lets us like model our systems and then predict how they're going to behave. So you can think of it like, how do we know that our car's cruise control is going to be safe? Like, how do we know that it isn't just going to, go unstable and run us off the road or whatever? And the way we do that is by representing what the car is going to do mathematically, and then prove that mathematical model is going to do what we want it to. And we can prove other things too, like if you get a gust of wind, that you're still going to go the direction you want to go. And so to prove that we have robustness guarantees in the face of uncertainty.
Or I think in our application would be more likely to be a gust of another robot coming and hitting you in autonomous, right? Yes.
Yep. Yeah, and also like battery voltage drop.
That's
friction
important.
in your gearbox, drift in your gyroscope.
So could something like this, obviously it depends on, I guess the bigger answer is probably it depends on the application, but could you use this to like make up for significant issues you may be having with the driveline, for example, if this is being used for driving? Like say, for example, one of your motors becomes unplugged. How much is this do you think this would be able to facilitate correcting for it?
So it's a trade-off, because Well, your controller can like work really hard to correct for whatever is affecting your robot to prevent it from doing what it's supposed to. And you kind of have to weigh whether you let the controller handle it or it's too big of an issue, like the entire half of your drivetrain's out. And like you're better off just, fixing the gearbox.
Right.
So I would say the best like balance there would be like if you have like small deviations, so like battery voltage, as long as it's not like a 5-year-old battery, and like you can expect your feedback control to handle that, and it'll like add more voltage to compensate or whatever.
Okay.
But if it's easier to fix it mechanically, please do so.
I agree.
Make it easier on your programmers.
Yes.
Yeah. So we're going to cover a couple different types of controllers. There's 2 categories. There's feed forward, and we're going to cover what feed forward means in a bit, and feedback. And we're going to cover each of these types. So feed forward, so I guess we'll get to that in a little bit. So feed forward is, so you're saying, well, I know how I want to get my robot from point A to point B. So like I have this trajectory I want to follow. And if I know how my robot's going to behave mathematically, I can say, well, I don't need my feedback control to be like, oh, there's an error in my encoder position. I need to correct for it. You can be like, well, I know I need to go from this encoder position to that encoder position. And I know how a voltage maps to what that change is, so I can back that out and be like, okay, given the change in encoder positions I want, I can figure out what voltage I want to apply. So instead of waiting for errors to occur before you act on them, you can proactively drive your robot to the destination and react faster to disturbances. And plant inversion is the most common way of doing this. So don't worry too much about the notation. This is just a standard form, and it'll be easy to explain algebraically. So we have a model that says, so x is things like our velocity. So we say like a flywheel that we have. We have the current velocity, and we have the input as a voltage. You can apply a positive voltage, and that'll accelerate it, so which means your velocity is going to increase, because you see that plus BU. And then the A will be negative, because it'll be like your back EMF. When you apply like 12 volts to a motor, and then you apply 0 volts, the motor slows down, right? So with a DC motor, it's essentially a generator.
Right.
So you think of like a flashlight, those old flashlights with the cranks on them, you like turn the crank and then it lights up a light bulb.
Yeah, exactly.
Right. So you can generate power, but it requires work to do so. And so that work is what's slowing down the motor. So like you're applying voltage to it, and that electrical voltage is being converted to mechanical work. Like that's what a motor does.
Right.
But it works in reverse. You can have mechanical work done on the system and generate a voltage. So if you were to like push your robot, you might have noticed how like you push it fast enough and things start lighting up. And the LEDs start blinking because it's a generator.
Yeah.
Right?
And if you have Falcons, you might see some other stuff too.
Oh yeah.
We won't talk about that though. We'll move on.
No. Yeah. So this is the general form for what these things do. So remember, use your input. X is your current state, where your system currently is, like your velocity or your position. So once you have a model like that, you can just solve for your input. And that's what we do here. We say, well, I know. So R is our reference where we want to go at the current time step. So we got K, and then K plus 1 is the next. So what this says is that we get the difference between like where we are and where we want to be. So like, so RK plus 1 equals ARK, and you just solve for U, and you get like B inverse times that difference between the two. And an interesting thing to note here is that say you were slowing the motor down with back EMF, you're just letting it coast down to nothing. If the reference is already following that, then when you do A times R, you're going to get RK plus 1 back, and then you get a 0. So you get B inverse times 0, and you have no input to apply. The system's already doing what it's supposed to, so you don't need to do anything extra. So that's one of the cool things about plant inversion, is that you can take whatever the plant originally did, plant being your physical system, and erase those dynamics and put in whatever you want, which might be your motion profile, like the trajectory you want to follow. And then so that was modeled dynamics. So we already know how the system behaves. You can also do unmodeled dynamics. So things like gravity, if you don't include gravity in your model. So like, you have an elevator and you need some holding torque to hold the elevator carriage up. Well, gravity is actually proportional to a voltage you apply. So you can just apply a constant voltage to offset gravity. And then your model and your feedback control work the same way. So if you know a little bit more about your external reality, you can incorporate that using extra feed-forward terms so that the feedback control has to do less work. And you can incorporate all kinds of things like gravity. You can incorporate gearbox friction. And you can also... yeah, I have an example later of other types of feed-forwards.
Okay, cool.
So we'll get to that later.
Yeah.
So that's feed-forward. So feedback is what a lot of teams like are familiar with. You have the PID controller, the infamous PID controller, where you have 3 different terms. You have your proportional term, your integral term, and your derivative term. So you can think of your proportional term like a spring, like a physical spring. Because if you attach a spring to some point, so say it's the point you want to go to, then you pull that spring, it's going to apply a force in the opposite direction. It's going to pull you back to that point, and it's going to be linear. And a P controller works the same way, where we have a proportional constant times the error. So it's some distance away from where we want to be. So you can think of a P controller like a software-defined spring that's pulling your system to where you want it to go.
It's interesting that you put it that way, because I know I as more of a mechanical person myself, that's the first thing I think of when I want to keep something in a particular location or dampen its movement, is to add like a constant force spring or some other sort of spring like that, especially with like elevators, for example.
Yeah. And like in the case of constant force pull springs, it's like your gravity compensation. So it's applying a constant force.
I see. So it's kind of like doing the same thing that what you're doing in this controller, but mechanically.
Yeah.
It's almost...
And you can also apply... That's the way feedback control used to be done. It used to be all mechanical.
Right. Yeah.
So like if you were steering a boat, you'd have like physical, like mechanical systems that would like figure out where, like what position you want the boat to point in. And then like, I guess, what is a good example? There's this old system called a flyball governor.
Oh, okay. Yeah.
And the way those work is as it spins faster, it like has these weights that move out. And when you think of like an ice skater that moves their arms in and out, when you move your arms out, you're going to start spinning slowly,
right?
Like more slowly. And you bring them in, you're going to spin faster. So a flyball governor works the same way, where you pull your arms in, it's going to go faster. And then if you put your arms out, it's going to go slower. And so if the thing is spinning faster, the arms are going to, with a flyball governor, they're going to go out, which is going to slow it down when it's going faster. And if it's slowing down, the arms are going to go in, which will speed it back up again.
Right.
So you have this negative feedback. It's always operating opposite of whatever the like disturbance is. And to keep you at some constant velocity.
But now that we're sort of in the modern age, right, we've replaced most of this with computers and control loops because of the cost and the relative ease of changing it, as opposed to building a new flyball governor when you want different activity.
Yeah. Or like you can even do electrical circuits with like operational amplifiers. That's how a lot of like the feedback gain in your microphone, used to use op amps and stuff to like amplify whatever signals coming in on the microphone, and like, using a transformer. And yeah. So that's how like proportional control works. So the derivative term works basically the same way. I know some people introduce it as like a damping term, but you can actually be more general than that. It's actually a proportional controller on the velocity. So so you could think of it like a software-defined spring pulling your velocity to where you want it to be. And you can do some math to prove that. You just plug in what your error terms are and then shuffle some terms around. So when you're doing motion profile following, that's what your two terms are doing. You got your proportional term that's on position, and then you have your derivative term that's on velocity. And so when you're following, say, a trapezoid profile, you have a term on position, a term on velocity. And as long as your motion profile is doing something that the thing can actually do, then it can follow pretty well. And we'll show that in a bit. So that is for linear control systems. So by that, I mean that, remember this equation here, it's everything a linear combination of variables. You have a constant times your velocity plus a constant times your voltage, and that gives you your next velocity. So with drivetrains, the actual model is nonlinear because you have a heading. Because remember those trig functions we saw in the odometry? So those trig functions make our model nonlinear, which means nonlinear control theory starts to break down a bit because it assumes a different form. And so Ramsete is this control law that we implemented last year that's used for correcting your drivetrain based on where you want to be on the field, your desired pose and your current pose. And it'll give you a velocity and angular velocity for the linear controllers to follow. So what we're doing here is we're taking our linear PID controllers on our wheels and we're augmenting it with this outer controller. So it's like doing higher level planning. And so let's look at 8.35. So the control law itself is not that bad when you break it down. All that first equation is doing is just rotating your error, like the difference between where you want to be and where you are, into the chassis frame. So instead of working with global error, you're working with error ahead of you and error to the side, and error in your heading. And then our feedback controls basically just proportional controls. You have your, so that K is a proportional constant, and you have times whatever your forward error is. And then if you want the robot to turn, then you have these other terms like K times the heading error. So you got similar proportional gains here. You just have some extra terms added in, like that third term in the omega equation. That's to help like deal with cross-track error. So that is like the distance to the side that you're away. Because remember, with two-wheeled robots or four-wheeled robots, you can't move your robot sideways directly.
Right.
If you could, that'd be easy. That's basically mechanical. But with two-wheeled robots, you have to like turn towards where you want to go and then drive that way. And so that's what that's doing. It's taking the error sideways and turning that into error that's forward so that other part of the controller handles it. And then I won't go into what any of the other equations are doing because it's not important. The funny part about the Ramsete is that some guy just came up with this equation and proved stability of it. There wasn't really any physical intuition behind it beyond it being proportional control or whatever. He's just like, well, it works. Off we go.
So not to labor this point too much, but what you're saying is that this guy basically came up with the concept behind it, tried it out a few times, jiggled some numbers around, and then it works?
Yeah.
Oh, wow. So as opposed to like
so
coming up with a mathematical proof and then just later seeing that it actually works in real life.
it's a blend of the two.
Okay.
So there is some creativity in the control law you pick, but there's also math to prove that it actually is convergent,
I see.
like globally. So because what Ramsete is trying to do is have a globally convergent control law. So if you think of like, let's assume for a moment you have just your left and right PID controllers. So if you were off of, like, say 2 meters to the left of your goal, and you're already at the end of your trajectory, like the PID controller can't do anything because it can't move sideways.
Right.
Right. So what we're trying to do is perturb it a bit, and which is what that omega term does, to like turn it and make that term what's called controllable. Controllability is this concept of like, based on where I am, I can get to where I want to go, like given admissible inputs, like like finite inputs.
Right. Hey, Tyler, real quick, actually, we have a message in the chat from somebody, my R squared. They're basically talking about a mechanism, right? And so this whole presentation so far, it sounds like it's basically focused on, we'll call like the 6-wheel, 4-wheel, 8-wheel style tank drive sort of robots. But there are actually, in WPILib, there are trajectory planning options for mechanism drive. Is that right? Or holonomic drive?
Yes.
Okay.
And actually, control for swerve and mechanism is in some ways easier than differential drive robots.
Because you do have the ability to do what you just said, is to be at the end of your, is to move sideways at the end of your trajectory.
Yeah, which means you can simplify your control laws a lot by just saying, I want a P controller on my X position, a P controller on my Y position, and a P controller on my heading.
Oh, that's true.
And you're done.
Yep, that's fair.
Yeah. And because your wheels are able to drive in arbitrary directions like that, like you can just have 3 linear controllers. And that's what we do in WPILib.
Okay, excellent. That's great to hear.
So the trajectory planning was originally designed for differential drives. So when you're planning a path for a mechanism drive to follow, you can actually ignore the heading on that trajectory. You can make the heading do whatever you want. It's a free variable.
Right, because your translation is independent of your robot's rotation in that instance.
Correct.
Yep.
And so that's what we recommend teams do, is to just generate a trajectory, but then just make the heading do whatever you want. You can make it a trapezoid profile. You could make it a constant value the whole time, because you're not limited to driving like in a specific direction like differential drives. Yeah. So consider this presentation like the harder case.
Okay, cool.
And so I've been talking about motion planning, but so here it is. So with motion planning, what you're trying to do is, rather than just changing your set point immediately from like 0 like radians per second to like 500 radians per second, like instantaneously, like the system can't do that, right? So like it's going to lag behind and eventually reach whatever your set point is. But if we change our set point only as fast as the system can actually move, then it gives us a couple of advantages. We can get a more predictable system because like the actuators are within their limits. So like the feedback control has more authority to keep you where you want to be going. So like your springs are strong enough to keep you within like your tolerances. And you can also apply feed forward, because now that you know, like I can actually go from like this current state to the next, I can calculate an input to apply that is actually possible, which means that not only is your system smoother and more predictable, but it will behave better and be more resistant to disturbances. And there's a couple different kinds of motion profiles. So we're going to cover 1 degree of freedom profiles first. And what a degree of freedom is like a variable, like a free direction you can move in. So like an elevator would have 1 degree of freedom because it can move up and down. And then a common profile we use for one degree of freedom profiles is a trapezoid profile. And so the top plot shows you your position over time, and the middle one shows you your velocity, and the bottom one shows you your acceleration.
Okay.
It's called a trapezoid profile because your velocity is in the shape of a trapezoid. And another thing to note is the acceleration is some constant value. So, and then there's another profile called an S-curve profile, which makes your acceleration more continuous.
So you wouldn't have
velocity.
You wouldn't have a constant acceleration. You'd have something more like some sort of other waveform of some kind.
Yeah, and if you look at the bottom right plot, you'll see it. Now the acceleration is a trapezoid.
Oh, okay, cool.
So with things like CNC machines, they use higher degree profiles because it lets you deal with things like jerk, where like the higher order terms you make controllable, the less vibrations you get when you move the thing around.
Right. And just for folks who may not be familiar with it, jerk is the rate of change of acceleration, the acceleration of acceleration. Is that correct?
Yes.
Okay, cool.
But with FRC, generally we only need trapezoid profiles.
Right.
Because if you remember the motor model I was talking about earlier, we are able to, so the input, our voltage, is proportional to our acceleration. So when we apply a voltage, it's going to accelerate. And when we're following a trapezoid profile, you'll notice that the accelerations are all constant. They're not like infinite values like they would be with like a step change.
Okay.
But that also means that now our voltages are also constant and finite. So theoretically, if you know what voltages to apply, you can have a motor follow a trapezoid profile perfectly with feed forward. So that's why we don't use S-curves as much, because a trapezoid profile is simpler to implement and like it's good enough.
Yeah. Well, I mean, like a CNC machine, you're hoping to get within a few thousandths of an inch, but if my robot could end its autonomous mode within 6 inches of where I want it, I think that would be pretty good, honestly, for a lot of teams, especially.
Like the margins of error in FRC are a lot smaller, so we can get away with a lot more.
Yes, exactly.
So that was 1 degree of freedom profiles. You can also plan maneuvers in any degree of freedom you want. An example of a 2 degree of freedom is your drivetrain. You have your X and your Y axes. So to get some vocabulary out of the way, so a path is a set of points that you want to follow. A trajectory is a time domain version of it. So it's like a path and like a time associated with it. So it's like this profile where you have like time progressing forward and velocities and positions mapped, whereas a path is just a set of points. I see some people mix those up. So with a 2 degree of freedom motion profile, the way we implemented it in WPILib is 2 types of splines: clamped cubic splines and quintic splines. So a spline is a curve where you specify your endpoints. So you'd start from like where you are and where you want to go, and it finds a smooth path between the two. So it like interpolates between them. So with clamped cubics, you can specify your start and end poses and then your intermediate translations, and it'll pick headings in between for you. Quintic lets you specify headings at every waypoint. So to say that again, you can specify waypoints, which are specific poses you want to go to throughout your trajectory. and splines find a smooth path between all of them. And I put a link to this presentation, which goes into more detail on like how that works.
And I don't know if you noticed in the chat, but someone with the same name as that GitHub repository is claiming to that be their presentation. So I'm going to put a link to that. I'm going to put a link to that in the chat for those who are watching now, if you want to go back and look at it.
So I'm including it here just so that like people have somewhere to go. But I'm just going to stay like a little more abstract because it gets a little more complicated than we care about, where you have to like fit a spline and then figure out how to like map time to it. And it gets kind of tricky. And his presentation goes into a lot better detail than I could. Yeah. So now that we've covered all of the different things, we've covered motion profiles and different types of those. We've covered feedback control and feed forward control. And we've covered localization. So now we know where we are. We know how to get between where we are and where we want to go. And we have a method of getting there in the presence of uncertainty. So now I'm going to show what that looks like in robot code.
So I'm going to put our face on the screen for a second while you go ahead and swap over to your environment to do this. And so as you're swapping over, Tyler, can you just give us a little bit of information about this is all available within WPILib or WPI? Is it lib or lib? Somebody asked that question actually. Is that a?
I'm not actually sure.
Okay.
I know a lot of people pronounce it like, I don't know, even I'm not sure.
It's kind of like
WPILib, but
it's like GIF and GIF, right? So, so anyway, while you're doing that, this is all available with WPILib. Is it part of like the standard distribution, or where would you go to find this stuff?
That's all with the standard distribution.
Okay, cool.
Like all these libraries are there. Documentation is online at docs.wpilib.org.
Okay, great. All right, so once we get the stuff up there, we'll swap right over. And just a reminder for everybody listening at home or watching at home, if you have questions for Tyler, you can go ahead and submit them into the Twitch chat, and we'll ask him. We're going through and doing them as we go with the presentation, as well as at the end. So if you've got a question, go ahead and just type !Q in the chat, and then we'll pick the question up and we'll ask Tyler at the appropriate time. So
yes, please ask questions, because it's hard for me to know, like, because I've been doing this stuff a while, it's hard to know like what the appropriate level is and like how much I need to explain.
Right. I think there's probably a good mix of people who are watching. There's definitely some folks who are this is something that they've worked with before, but I think that now and especially later on, we're going to see a lot of people that are new to motion planning. And I think that, like you said before, most people are very, very new to the simulation aspect, or the model-based validation part of it, like you were discussing.
Mm. Yeah, so I have the project up now.
All right, cool. We'll just send it over there.
Are we good?
Yes, you're online.
Cool. So we're going to show like all these different components. We'll start with the sensors. So you have, like, we're going to assume that our robot has 2 encoders and a gyroscope. So we got your 2 encoders here. And then we got these A and B channels for each of them, right? For your left and right side of your robot. And then we have a gyroscope. So I put an analog gyroscope here because our simulation support supports it better than the other ones, like an ADX RS450. I highly recommend using some of the analog digital gyroscopes. My team has had good experience with those because like they're digital. Like the issue you get with analog analog gyroscopes is that you got to like shield them well. So you got to like sometimes put them in a metal box and like shield the cabling. But you don't have to do that as much for things like a NavX or an analog digital gyroscope or the Pigeon, like any of those. And so we got 2 motors, and then so a lot of the code here is all declared inline, mainly because it's just a lot less typing to do so. So we can basically just declare everything in order, right? We got the motors, our sensors, and then we got our kinematics, which is we're going to use for localization. So that the pose exponential stuff you saw earlier, so that's represented by the differential drive odometry object. So we give it an initial heading, like when you start the robot. And then we have our controllers here. We have Ramsete, and then we have our 2 left and right PID controllers. I made this just so I didn't have to go figure out what some feedback controller gains were. So you'll see this stuff in 2021. But
yeah, so like a bit of a sneak peek then.
Yes, but you can find your feedback control gains using any other. You can use the FRC characterization tool that's provided, and that'll give you some feed forward gains, as well as feedback gains, like automatically based on the data it gathers. It basically just drives your robot forward and backward, and then spits out some feedback gains for you.
Oh, okay.
Yeah, and so you got your P gain and your I and D gains 0. The reason for that is a velocity system. You have only one derivative involved. You have your acceleration input, your voltage, and your state is a velocity. Because there's only one quantity being controlled there, you don't have like position and velocity. You only need one proportional term. And then we make a trajectory that we can use for later and make a timer. And then this is some logging and you can log however you want. You can open a file, write some CSVs. You can use network tables to do your logging, and that'll show up on a dashboard for you. And then now that we have all of our objects declared, then we initialize our encoders and then say and specify a distance per pulse. So encoders are measuring pulses. So you've got your A and your B channels, and it's counting how many times those channels go up and down from 0 to 5 volts and back. And so as you spin it, you get 360 pulses per revolution. And you need to tell it how many pulses corresponds to a meter traveled. And so that's what that constant refers to. It'll do it'll convert from ticks per revolution to number of revolutions. And then from revolutions of the gearbox to revolutions of the wheel. And then you just do pi times diameter, and that gives you your distance traveled on the ground. And I can pull up that constant real quick. So you got 2 pi times the radius. That gives you your circumference. And you got the gear ratio, and then you got the number of ticks per revolution. So now that we've had all their stuff initialized, now we just need to do an autonomous mode, right? So we initialize our odometry and saying we're starting at 0 meters, and pointing at 0 degrees. And then our gyro is also starting at 0 degrees. Then we generate a trajectory from where we are right now to where we want to be, which is 4.8 meters in the X direction and 2.7 in the Y direction, and pointing in the same direction as you were before. So what you're going to see is...
Can I ask a really, really quick question? How you're doing tenths of meters. How accurate do you think that this truthfully is too? If I specify down to a centimeter, how likely I might actually hit that?
So in my experience, you can get within a centimeter or 2.
Oh wow, okay.
If you're really good.
Yep.
And that really comes down to how good your feed forward is.
Okay.
So if you have a really accurate model, and and then really well-tuned feedback gains based on that model. But these numbers are like this because they were copied directly from my team's robot code, and those originally were in feet.
Oh, okay.
So yeah, they got converted into meters because with controls, it's easier to work in SI units than imperial.
Right. Factors of 10 and all that.
Yeah. So we make a trajectory. This one goes from 0, 0 to some other point. So you're going to see an S curve looking shape in the XY plane. And then when we do our periodic autonomous call, we update our odometry based on our encoder measurements or our gyroscope, and then our encoder distances, and then it magically turns those into your pose. We get a trajectory state. A trajectory state includes things like our X, Y, and heading on the field. It also has our robot velocity and our angular velocity. And so that tells us how we want the robot to be moving at the next time step. Then that'll give you the movement of a unicycle. And by unicycle, it's like, a one-wheeled robot that can rotate. Because that's why we made this kinematics object here, so that we can convert a unicycle like chassis stuff into differential drive. So you got your left and right wheels. You give it a width, and then it converts that into left and right wheel speed. And then once you have those, then you throw that into Ramsete. You give it your current pose, and then you give it where you want to go. And then it returns for you the a new set of left and right velocities. So you give it a reference velocity, and you remember from the presentation how it has the desired one and then a corrective term added on. So if you're lagging behind, it'll increase your velocities to catch up. And those become your new set points for your PID controllers. And then we do some normalization, because if you're wanting a velocity that is faster than the robot can achieve, you can get some really funny behavior, like that has to do with this thing called actuator saturation. So if the robot can only go 5 meters per second and you tell it to go 6 meters per second, there is no voltage you can give it above 12 volts that will, below 12 volts, right? Because you only have 12 volts available to get there. And when that happens, now your left and right wheels are going the same speed. And so now you've lost authority on your turning.
I see. Okay, that makes a lot of sense. That would what you've described is my life, and when I was in high school trying to get my robot to drive in a straight line with two encoders.
Yeah. So you always got to make sure that you have the control authority available to do what you need to do.
Exactly.
So that's what this does. It normalizes your left and right velocities, reduces them proportionally so that you get the same ratio between the left and right. So you're going to get the same turning radius, but your forward velocity is going to be lower, so that the fastest wheel will be attainable. We'll have an attainable velocity. And now that we have a velocity reference, we throw that in as the reference of the PID controller. We give it an encoder rate, and we put that directly to the motor. Right, so we got update our odometry, get a point from our trajectory, turn that into a desired velocity for left and right, and then give that to the PID controller, and then it does the rest.
Okay, so I noticed that we talked about how all the matrix transformations and stuff works, but none of that's featured in here, and that's all taken care of just by that Ramsete function you've got in WPILib.
Yeah, it's all in the Ramsete function and the odometry class. It handles all of that internally. Okay,
wow.
So, and that's kind of why you haven't really seen teams besides the ones you see on Einstein every year, because they would usually home grow their own trajectory implementation,
right?
Because it took all this extra mathematical knowledge to do it.
Well, I do remember a few years ago, Team 254 released some stuff on that, I think in like around 14, 15, 16 era about how that all worked. And now the same feature set has been integrated into WPILib. Is that accurate?
That's correct.
Oh, cool.
And I believe some of the internals are based on 254's implementation.
Oh, cool.
Because like the way that it's mapping so you have the spline that moves throughout space, and then that turning radius you get, we represent that as a curvature. So it's like how curvy the line is.
Right.
And we're trying to find if you were to take each point along the trajectory, like every 5 milliseconds, you're going to end up with a whole lot of points in your trajectory. So it's going to take like a lot of computing power to actually generate that. What it does internally is it will say, well, I can approximate this with little circular arcs to match that curvature. And so it'll match the turning radiuses, and we subdivide them to get within a certain tolerance of error in the X and the Y.
Okay. And just out of curiosity, that I'm sure people would ask, right, is that tolerance for error you've just stated, is that a user-defined thing, or is that part of the library? And how did you guys come up with that particular value of the way it is?
So that we did just through experimentation, because there was this trade-off between like how much error you're tolerating versus like how well behaved the trajectory is, or how many points you're sampling.
Right.
Because like we also support constraints. So we can say, I want this trajectory to slow down around turns. Or it's like you can specify a centripetal acceleration. You can specify differential drive constraints, so that instead of it only being the center velocity that stays under a maximum, you can say, well, I want both of the left and the right wheels to stay under that. So you don't have to do the scaling like the Ramsete thing did.
Right.
And then, yeah.
So another question I just have. So like I said, I am not a excellent programmer, and I don't program my team's robot. So a lot of this is, sort of library. You've got a lot of function calls going in here through the WPILib that takes care of all of the extreme heavy lifting, but there's still a fair bit of code that you wrote yourself to do all of the scaling of the inputs and stuff like that. Why did you guys when you're developing WPILib, why did you decide to go with this approach as opposed to just creating one humongous function that just takes in like 5 or 6 parameters and then make your robot drive, hopefully, right?
So we actually have in the command-based framework.
Oh, okay.
There is a Ramsete command where you can just throw in the PID controller instances and the motors and the encoder and the gyro getters, and it does all of this for you.
Wow. Okay. That's pretty cool.
It's just that I don't know command-based, so that's why I'm not showing command-based today.
I see. Okay. That makes sense to me.
Yeah, because command-based is nice because it lets you specify state machines and stuff, but my team does them kind of manually.
Okay.
And you can get into philosophical discussions on why. But, yeah.
Yes. But so the feature is sort of more wrapped up more tightly in command base, but it's all none of this is terribly earth-shattering here when you're just using this right here.
Yeah, and we do need to add an example that isn't command-based that shows this. And we're still working on the logging stuff that you've seen, because we're still trying to work out the best way to do it.
Okay.
Because we have network tables, and that'll send values over, but it only updates every like 10 milliseconds. And for higher data rate stuff, you need to capture all the data, not just whatever the data was every 10 milliseconds. So we're going to work on that. Because yeah. Oh, and I forgot a component here. So this is a constraint you can do. So you can give it whatever your max velocity or acceleration is, and then when it generates its velocity profile, it's a trapezoid along the trajectory, the spline.
Okay.
So you can think of it like a trapezoid profile, and the curvature So the linear velocity is going to be a trapezoid, and then you add turning on top of that. And that's basically all it is.
Very cool.
Yeah. And I ran into some issues today with the simulation backend, but I do have the simulations from my robotics team that I can show.
Sure.
Let's see. This is the time domain plots.
Oh, here we go.
And then
We'll put you right back
I'm
on.
grab the trajectory it's trying to follow. And it's that trajectory we saw earlier, where it starts at this point and then it goes over here.
Actually, would you mind just doing that one more time? Just show everybody what you just pointed out. We were changing over some things while you're swapping.
Okay. So if you look at so this is the same trajectory we saw earlier.
Right.
Where you start at 0, 0, and it goes to that other point we specified.
Okay. And
so
this is like a position in real space, right? In meters.
So
okay.
X, the X position on the X axis, and then the Y position on the Y axis. The orange is the trajectory we wanted to follow, and the blue is where the model thinks it is.
Okay. Wow.
And at least based on that, it's pretty darn close.
You can barely even see the blue underneath that.
Right. So this is using some libraries that we're working on for 2020 with state space. So it uses linear algebra to provide a more succinct, compact notation for mathematical modeling. And so you can throw in your feed forward gains, and then it will build up a model, and then you can simulate it. And then if you look in the time domain, there's a couple different things here. Here's the velocity graph on the top right. So you'll see let's maximize that. There, can you see that?
Yes.
Okay. So you see the red line from the right wheel velocity, and then you have the left wheel velocity at the green. And then you can see the velocity tracked pretty well.
Yeah. So what?
But we'll get into why it's a bit noisy in a bit.
Okay, go ahead. I was just about to ask that question.
Okay. Yeah. So with the simulation we did, we said, well, now we have an idealized model, but like we can include extra stuff. Like we could actually model voltage drop. We could model friction. We can model the fact that our control loop doesn't run at the same time step every time. Like it jitters a bit. So it'll be, every 5 milliseconds, but it could be off by a millisecond or two in either direction. And so if you look at this, you can see how the battery voltage drops as you're applying more voltage to the system.
Right.
Right. And then when you let go, it goes back up. And you'll see it goes above 12 volts a bit here because the thing is slowing down. And remember, motors are generators. So when you're slowing down, you're generating voltage.
Oh, okay.
So for a little instant there, you have extra voltage. Yeah. And then some of these are just like quantifying uncertainty. So like an error covariance is just saying, this is how certain I am and where I think I am in X and Y and all the other ones. And so we're using state estimators to like clean up some noise from our sensors. And we can represent mathematically how certain we are that what we have is accurate. Let's see. And I guess I'll show you a little bit what what the code was that generated those.
Oh yeah.
And I'll be posting this code on GitHub later, by the way.
Excellent, because we just had a question in from Mr. R Squared asking if you would be saving that example. What should we look for GitHub to find you?
GitHub.com/calcmogul. CALCMOGUL.
Okay, mogul, got it.
Yeah, so this is the drivetrain controller. And so this is starting to get into some of that model-based testing that I was alluding to. So the way we architected our code last year was we had our controller and our system separated so that we could simulate our measurements and our control inputs and like shim them out of our robot code. In future years, we'll hopefully be able to just like use the encoder objects directly and just mock them out. So we make our drivetrain model, we set our initial position like the other one, and you basically just have a while loop that simulates it forward. You have your time step, DT. Here's where it adds the noise to the scheduling. And then you've got generating our measurements.
Can I actually really quick just have you step back to the noise part there? Are you just adding a factor of like 0.001 to it just as it goes, or?
So with noise, the way you quantify them is with a mean and a variance.
Okay.
So the mean is the average. That's like the center value with no noise. And then the variance tells you how confident you are in like that mean is like that. If you were to sample the system, how certain you are that you'd get that mean.
Okay.
So the more higher variance you have, it's like a bell curve. And the higher your variance is, the more spread out the bell curve is. And so what this is this is a standard deviation.
Oh.
It's easier to think about those.
Okay, that makes sense to me, yes.
Because variances are squared units, but people don't think in square units.
No.
So we're just adding on like, this is like 0.1 centimeters.
Right.
Or actually this 0.1 milliseconds. And we got that value by logging what our controller update rate was and saying, the noise is like about this much. And then we throw that in our testing. And you can do that with any of your sensors with measurement noise. You can just sample some data and then look at how noisy, and then say, well, the error bound looks about this much. And then you can use the random libraries in Java or C++ to generate like noise for you.
Oh, okay.
Throw it in. And some of these are just wrappers from the state space libraries. And And so we have our local measurements. We add noise to that too. We have multiple values here because you have one for each of your measurements. Because remember, y is a vector. You can have multiple measurements at once. You got your standard deviation of your gyro and your two encoders.
Right.
And then we tell it what our measurements are. And then we tell the controller to update. And that's going to do two things. It's going to push our model forward. So like the odometry thing we saw, it's going to take those measurements and like project it forward based on our new information. And then that's also going to calculate our feedback control gain, our input voltages. And then we just feed those in. And then this bit is just calculating what the voltage drop is. And that's just Ohm's law. You take your battery voltage, subtract off the current drawn by your motor times the battery internal resistance. And you just do that for all your motors.
Okay.
And that's how you can get voltage drop. And by simulating voltage drop, what that gets you is the fact that like when you try to accelerate, you're going to lose a bit of control authority because you no longer have 12 volts. It's going to drop a bit. So you can test like based on your controller tuning, will it still be aggressive enough to hold on the trajectory?
So is this also feeding forward the voltage drop, or is it just simulating it for this instance?
In this case, it's not feeding forward the voltage drop, but you could totally do that.
Okay, cool.
The way you would do that is you take your voltage that you have and you just divide by the factor that you get in the drop. And that will give you a higher voltage to compensate for the battery voltage going lower.
But then with that higher voltage, you then put the voltage drop in again, and then, no, never mind. Sorry.
Yeah, but that's the issue, right?
Yeah.
So the more you compensate, if your battery internal resistance is high, you very quickly get into this situation where there is no more control authority to give.
Yeah.
Because your battery voltage just tanks. So that's why it's important to do a couple things to make sure your battery is securely connected, to make sure all your motors are well connected, to make sure you properly spec your motors so that they're not drawing too much current.
Right. And not to go too far on that particular point, but on Wednesday, tomorrow at 4 o'clock, we've got a presentation on just how to do that by Professor Ken Stafford from WPI. So, all right, hashtag plug. Sorry about that. Go ahead, Tyler.
Yeah, no problem. So yeah, and you'll notice here how actually I think this is that correction term I was talking about. You take the actual voltage and the idealized voltage, and that scales it back up.
Okay, there you go.
And then this is how we project the model forward. Because there's two ways you can work with controls. You can work in the continuous domain, which says my system is changing all the time, like an electrical circuit, and like it's always getting updated. And then there's discrete, where it only updates like every 5 milliseconds, and then the inputs are constant between that. And for our controls, we use continuous models because of the fact that the DT varies. And when it varies, like you can get a more accurate prediction by including what the DT was. And you can rediscretize and then essentially reduce the amount of noise. And then this is just how you can turn a continuous model into a discrete one for nonlinear systems, like a drivetrain.
Cool.
And I guess I'll plug one thing quick, and that is that you see a lot of these terms like Runge Kutta.
Yep.
And like things like that.
I saw that, and I wanted to ask, but I didn't know how to ask what that meant without looking like a total fool.
Yeah. So you'll notice this a lot in controls where you kind of just need to pick a name for something.
Okay.
Especially in like higher level math, you get a lot of these higher level concepts that have a lot of stuff underlying them, but you need a way to concisely convey that idea to your fellow mathematicians. And so you can say, well, this is a method for like with the odometry thing where I get my encoder positions and then I turn them into global ones. And like that whole process, you want to encapsulate that into one handle that you can like tell someone else and they'll know what you mean. But the tricky part is you got like all this jargon and you get to a point where you're throwing these terms back and forth and people have no idea what you're talking about.
Yes. Yep. So it's basically like naming this. It's giving a name to something which doesn't mean anything to the layperson, but in common usage, it means something that's very complex to discuss.
Yeah. Okay. And like in this case, this was named after two guys. Their last names are Runge and Kutta, I believe.
Okay.
And so you see that a lot in math where they're like, well, I made this thing and we need a name. And like their last names are as good a technical term as any.
Might as well, right?
Yeah.
So, let me stop me if you're going to cover this, but I'm kind of curious. Did you guys experience what was like the not sound like a judge, what was like the failure mode you guys experienced when you were testing this or validating this model, right? Like, how do you have any like examples of where you saw like your model didn't line up with what you'd expected it would be?
Yeah.
Okay.
And that goes into how we modeled the velocity dynamics of the drivetrain.
Okay.
So the mapping from the voltage inputs to how the velocity changed. And we were originally going to use just math to figure out what the model was, because you'll see this like where we make a mini sim and like say that it has 3 motors in the gearbox, and then we like get the motor currents and all that and compute all these constants and like figure out from first principles how it should behave. But it doesn't always work out that way,
right?
Because you have friction or efficiency, things like that. So what we did instead was we used the FRC characterization tool, because it supports 2 modes. You can do linear and angular. And drivetrains, being a 2 degree of freedom system, has like 2 different states. You have your left and your right velocity, and they're coupled. like they're not independent.
Right.
Like if you were to drive the left motor, the right side's going to move a bit.
Yes.
So what we did for that was we used the characterization tool, ran it forward. We got a set of linear KV and KA gains. I guess I'll show what that is.
Yeah, I was going to say, because the characterization tool, I knew about it because we were doing this presentation, but I didn't really know it existed until just about that. What is that all about?
So what we're trying to do with that tool is this guy Eli, who's been helping the WPILib team a lot recently, he came up with a feed-forward model for DC motors, where you can think of it like the velocity, like the back EMF. So like when you like let go of the motor, it'll slow down. Well, you can apply a voltage in the other way to offset that, so it stays at a constant velocity.
Yeah.
And then you can also add an extra term that says, well, if I'm accelerating, like this is how much I'd have to add to achieve this desired acceleration. And just add those two together, and that's your voltage that you need to apply. And so what that tool does is it figures out what this KV and KA terms are.
Okay.
Or I guess underscore V and underscore A, right? There's also a page on an FRC docs that explains this in more detail. And it has a static friction term as well. So we have this model here. So this is for the linear case. So you can turn this into that form we saw earlier with the AX and the BU. And you get that, let's see, V plus 1 over KA U. So you just plug and chug, and then you get that the acceleration you want is this back EMF term, negative KV over KA times your current state, and then plus the input. So that's how we made our model.
Oh, okay. That makes sense.
Yeah, and then the tool gave us those gains. Then you do the same thing for the angular case. So you have it spin in place. And the reason you do that is because your robot's mass is coupled to your moment of inertia. You can think of it like angular mass. And for robots that have a lot of mass in the center of rotation, like you can get different results for these gains. And then once I had those two models, I just threw it into Wolfram Alpha, spit out a model that incorporated the two.
Nice. Oh, so you didn't even need to do all the hard math parts that we saw earlier. You just let the computer solve it for you.
At that point, it was just doing algebra, and right. I really didn't feel like it.
You know what? I think there's a lot of people who would agree with you on that.
Yeah. And then I just stuck that in a function, and that was a model. And then we did have to retune it a couple times because we had a climbing mechanism that was sometimes on our robot, and when you took it off, the drivetrain controller behaved differently than if it was on the robot.
Oh, okay.
So, and you'll start seeing that when you're chasing like higher and higher accuracy, is that your controller gains get more aggressive, and small changes in your model can have a large effect in how your controller behaves.
Right.
Because you start getting into like smaller and smaller margins. And so that was a lot of our struggle, was making the model accurate, because our sims said that, well, our feedback control is working okay. Our going from our sensors to our odometry was working fine. Now we just need to make sure that the model matches reality, and then we're set.
Right. So I obviously, like I said a couple of times already, not a great programmer myself, but how much of this did you end up working on before the build season started? Like, is this what you described as a project within the scope that someone could complete within the 6 weeks and still have everything else in the robot programmed?
If you were to write all these libraries from scratch, probably not.
Right.
Because we've been working on this framework for like 2 years now.
Wow.
And like I have a good group of like 4 or 5 students who I've been grooming to be controls gurus. And yeah, so it started with us doing state space in Python and then having it spit out controller gains we throw in our code. And then we started getting into like, you can do all that math on the RoboRio, turns out. It's actually not that expensive to compute. So we started doing all the modeling in our robot code itself. And that started lending itself to using that in the unit test too.
Wait, so your team actually does unit testing of the code?
Yes.
Wow. Okay, that's pretty good. I think I would say most teams probably don't do that. Their unit test is to hit the upload button and then see what happens. But
yeah, because it really is a lot easier if you have the actual robot.
Yes, that's true. But that's
the main reason we did it is because you see this in both software and mechanical, where they're always trying to push the boundaries.
Right.
And in this case, they didn't have the robot done like to give us enough time to test. And so we're like, well, we can model everything mathematically and at least make sure our logic is good.
Yeah.
And that caught a lot of bugs, actually. like all of the control stuff is unit tested, and like all the models are, and the feedback control and the sensors. And this last season, the one thing that didn't work, which was the autonomous mode where you actually string all the actions together, wasn't working because that was the only thing that wasn't unit tested.
Oh no.
Yeah, I know.
Oh.
Yeah.
Yep.
I mean, we had driving. It's just we couldn't get the turret working in time.
Oh, yeah, that makes sense. Okay, cool. All right, well, before we go into a few questions, do you have any other stuff you want to present to us on the screen here?
Yeah, I can bring up a couple things.
Okay, cool.
So one thing I would like to bring up is that if you do want more information on the math, there's a book.
A book. Ooh.
And that's also on my GitHub at the same handle I gave you earlier.
Oh, wow. So you've actually written a whole like textbook sort of thing on this whole stuff?
Yeah, because what I found, like ever since I was a student in FRC, is that a lot of the control stuff, when you build it up incrementally, it's not that bad, but it's really hard to get all the information in the same place.
Yes.
And actually presentable. So that started in like 2015 or so, where I was like, I need to document this. So we have, like all teams do, they want to make resources.
Right.
And in this case, I was taking some controls classes at UC Santa Cruz. And so I was fresh off of all these controls classes. And I'm like, hey, this stuff is pretty neat. I want to teach that to my students. And that's what I did. And luckily they were patient with me.
So, and you said you could find this at your GitHub?
Yes.
Okay, cool.
And it's the same name as the thing there. I think it's pinned to one of the top repositories.
Okay, cool.
Yeah, and then I'll include links in the presentation README as well to my GitHub, and yeah, and that should take people through most of the stuff, I think.
Very cool. All right, well, with that said, I think we're going to move on to doing a couple of quick questions here. So again, if you've got any questions we want to ask Tyler, we've been poking into the chat and asking questions throughout the whole presentation. But again, if you've got some more you want to hit up, just go ahead and type it into the Twitch chat with !Q. And if all looks good, we will take it and put it up on the air. So we got one question here coming up. 1 second. Let me just get that set up while I get my ramshackle programming here all set up. Okay, cool. All right, so this question comes in. They're asking this about the characterization tool that you discussed earlier. Could you use the characterization tool for things other than drive lines like arms or elevators?
Yes, you can.
Oh, cool.
It supports flywheels, elevators, and single jointed arms as well. And so it'll estimate things like with the single jointed arm, it'll estimate your gravity, like the amount of holding torque you need.
Wow. So again, as a bit of a neophyte, if you use the characterization tool on an elevator or an arm, or say an arm, like you were saying, what would you actually gain from doing that? Would you be able to basically just actually take the real arm, plug it in, and it suddenly works all of a sudden?
Yeah, pretty much.
Wow. Okay.
Yeah.
Why don't more people know about this? I think they'd be pretty excited for it.
Right. It's kind of hard to get the word out, like that all these tools exist.
Right. I mean, not to go too deep into this sort of discussion, but I know there's a lot of teams that are working very hard trying to get the robot done and get their code working at all. That it's a challenge to get people and teams from that point to the next step where they can actually start to improve and get significantly more skill in what they're trying to do in this.
Right. Because like unit testing won't help you if you can't get like a basic drivetrain moving and that sort of thing.
Yes.
Like you need to build up to that.
Yes, exactly. But what I found is that once you reach that point, once you sort of cross that barrier, then there's no going back. You're good to go from there. It's really, if you've got a stable group of programmers or people who can pass down their skills, like you've been describing with some of the students on your team, then that's good there.
Yeah, and I guess the goal is to get everything self-perpetuating. Because like now I have a good core group of students who can help teach the new ones, which means that I don't have to focus so much on teaching people like how to program because we've got a good curriculum built up to actually do that.
Right.
And so we can focus on teaching the higher level control stuff and pushing the boundaries.
Okay, so you've kind of like, not to say outsourced, but you've distributed the load of bringing people on board, get that all together.
Yeah, it's like pushing decisions and things to the appropriate level.
Yes.
So that you can empower your students to help.
And this is a little bit of off topic, but I'm curious what your input is. I know that some teams are very eager to take people who maybe don't know anything about programming and bring them FRC programmers. And some teams basically say that, this isn't where you learn Java. This is like where you learn robot control theory. And they kind of expect you to learn Java either on your own or outside of thing. What's you and your team's perspective on stuff like that?
I think there is some truth to that because it's somewhat difficult when you're in the build season to teach them the basics of Java or C++.
Yeah.
And also have them implementing stuff on the robot. Because if they don't have the fundamentals of the language, in some ways it makes the robot stuff even harder because not only do they not have the tools they need, but they don't have the idioms they require to implement it effectively and easily.
Yeah.
So like essentially they're going up they're climbing the mountain on the steep side, right?
Yes. No, just starting off on the Black Diamond Trail,
Yeah. Whereas if you were to teach them like how to program with the modern idiom, then things become a lot easier because like a lot of the legacy instruction from the 90s, like you don't have to worry about that and they can just focus on getting work done because that's really what a programming language is. It's a tool.
Right. Yeah, that's one of those things that like, I have to sometimes explain to folks is that like it's not so much about learning Java, right? It's about learning how to use the tool, which is Java, execute what you want the tool to do, right? Like teaching someone how to make a mill move or how to turn the spindle on or how to move a piece of metal across an end mill, that's super easy. But teaching somebody how to hold a part to within 0.2 of an inch tolerance, right? That's the real skill and the part that people actually care about.
Yep, exactly.
Great. Cool. All right. So, actually, we just had someone in the chat at MR Squared. You've been talking a lot. They mentioned that they're a little new to control theory and that they had a little difficulty going around the documentation that you all provided through WPILib. Can you guys can you give me where people should go if they're interested in this and want to learn more? Where in the documentation suite?
Well, there's a couple different aspects. There is a trajectory tutorial.
Okay.
So that'll take you from nothing to building up your odometry and your trajectory stuff and like to a robot that moves and like follows the trajectory well.
Okay. Where can we find that?
So that is, I don't have my browser open. Bear with me while I open up my browser so I can dig up the link. It's kind of a long one.
That's okay. Well, if you can't tell me the link, that's okay. But where's the?
So they are all on docs.
Oh, sorry. I think you cut out there. Would you mind saying that one more time?
All of the pages are on docs.wpilib.org.
Okay, great.
There's a search box, and you could put in like trajectory tutorial, and that'll pop it up for you.
Wow, cool. And that should bring you through sort of the more basic stuff that even more basic than what we talked about today, all the way up through getting to this point.
So that will get you working with the trajectory stuff.
Huh?
We also have, we mentioned a couple like books to like learn Java or C++.
Right.
In the getting started section. And I guess also that we're always looking for feedback. So if something that we like, if you read the tutorial and you don't understand it and like you're frustrated, then let us know so we can improve it, because we understand the stuff. So whatever we write, like we don't know how to bridge that gap necessarily if we've been in it for too long.
Yes.
So we need fresh perspectives to be like, hey, I don't understand this because you didn't explain that. And then we can expand it and make it better for everyone.
Sweet. Cool. All right. Yep. And chat, they just linked that docs.wpilib.org. I believe I've actually swapped between lib and lib multiple times today, so I apologize to whoever has
fair.
who has a particular affinity for one or the other. All right. Well, before we head out, Tyler, do you have any last things you want to mention or say, or any last tips we have for anybody who's thinking about using either the trajectory planning or creating their own model to validate their own simulations to validate their own models?
So I would highly recommend joining the FRC Discord, because we have a lot of highly qualified people on there that can help walk you through it.
Okay.
And it's like, the programming discussion channel, we're always on there. And also I'll include links to like my team's robot code, because examples are always nice to have.
Yes.
Yeah. And also that PDF I showed, that'll give you like a lot of the introductory material. So once you start getting to actual application, you'll have a framework. And then once you get to that point, you can come ask one of us and we can take you to that next step.
Okay, fantastic. All right. Well, with that said, Tyler, this has been, I've honestly learned so much today that it's kind of funny. I don't even know what to say. It's a lot more than I was expecting to learn. And for someone myself who went to school for mechanical engineering and is now an event manager and stuff like that, I was shocked at how much I was able to grok from your presentation. So thank you very much for doing this. And I hope that everybody watching at home learned something as well and was able to take something away from it.
Mm-hmm.
All righty, very cool. So with that said, we're going to sign off from here, but we're going to be back at 6 o'clock. That's in about 15 or 20 minutes or so. We have our next presentation coming up. That's going to be using off-the-shelf or COTS resources to improve your competition performance, and that's going to be presented by Ben Martin. He's from Team 225 TechFire. I'm really looking forward to that one as well. But Tyler, thank you once again for your time today. I
was glad to be part of it.
Yeah, and I hope more people are aware of some of these tools that WPILib has to offer, because this is just the tip of the iceberg. I know that there's all these different things you've discussed. We have 2 more presentations about WPILib that are going to be happening this week. One on machine learning and one on the FRC vision and using Raspberry Pis, as well as desktop simulation of robot code. That's all going to be really cool. So make sure you don't miss out on those either if you're in roles. So. All right, with that said, thank you all so much, and we'll see you in just a few minutes.